Okay, so today, we're going to start the routine. So on Tuesdays, I'll talk about something in class. Oh gosh, yeah, we have a lot of auditors. Sorry about that. Okay. Um, so on Tuesday, I'll talk about something in class, and we'll have like a little lab experience, collab notebooks and stuff. And then on Thursday will be your presentations, your project presentations. So that'll be the routine. So welcome to the first Tuesday. Okay. And um, And so we're going to talk about the first experimental method I want to talk about today. But before we start, I just want to check in on everybody's house. You have a homework assignment due Thursday to, do a little 1 or 2 page write-up of what your project proposal is, project-based homework assignment. So the four of you work on a team to make this. How's that all going? Any questions? So there were 3 questions that came up from last night that had to do with research. I'll just call on people. And this is what I'll do through the day today. This is the secret reason for me to ask you to send questions, because then I can call on you to ask your question. Is uh, Kev Cavalia here? Cavalia, yes. What was your question?
I was reading the 3 papers that were mentioned for week zero.
Yeah, the research papers. Yeah.
It just opened up several questions in my mind, like what do authors mean by important questions? It's kind of contextual in nature and very much vaguely presented there, but it might even mean like Nobel Prize winning questions or like even small questions like just finding out what the LLM's last layer does.
Yeah.
For our time period of like 4 months of a semester, what's most feasible for us
Well,
to
you could win a Nobel Prize. No, that's all right. I think that's what Hamming is suggesting, is that you guys should be ambitious. And he says, do top shelf research, do high quality, the best that you can, right? There's no reason to compromise. I think that it's definitely true in our field, where I don't think that people are in academia in computer science for the money. There's other ways of making money in our field, right? And so, I don't know why you're hanging out in academia. If you want to make money, you go do some other things. Um, and so so while you're hanging out here, why not be as ambitious, intellectually ambitious as you can? So what is high quality research? It's a taste thing, but I think that one rule of thumb that I like, it's not universal, but I think one thing I like to ask is this something that you would want to teach people? Like 10 years from now, when you're teaching this field and you're going over the history, or you're going over the basics of the field, and you're saying, this is what you need to know. Is this piece of research that you're doing right now, is this something that would be on that list? Is this one of the top things that you've got to cover because it's so important for people to know, right? If it is, it's probably pretty important research. It's probably pretty important. If it's not, if you're like, yeah, I don't know why anybody would talk about this in the class, then maybe you're doing something more incremental, which is okay. 99% of stuff is more incremental. So it's hard to find something foundational, like the kind of stuff that Hamming talks about. But to me, that's what it means. There's probably other ways of talking about it. There's other research that you would never teach in a class, but it's so impactful for some reason, that changes the world. Like, I don't know, if you discover something about how to make computer chips or something like this, well, maybe it's too specialized and you don't actually want to teach it in a class, but it could change the world because computer chips are so important, or something like that. So there's other reasons that research might be important, but I like I like imagining what a future syllabus looks like in 10 years. And if your thing is at the beginning of the chapter, then it's probably pretty important. Make sense? Okay. So, Jasmine had another question. Something about small worlds and something like that. Jasmine, what do you want to ask what you were asking? What were your thoughts there? You had a few thoughts.
I guess the first was like what makes like a task feel like easier to evaluate than like or what makes a task like valuable? Like if someone asked me like did you feed my plants or like did you feed like a baby or something like that? Like it's kind of like you did it or you didn't do it. And then there's other like kinds of like research questions where it's like much more like abstract, where it's like, what's like a sufficient definition of beauty that just feel like very intractable for some reason.
Yeah.
So I guess like what are some like intuitions you have for identifying like a question that is like tractable, like is like
It's
things you
tractable.
can take action on, I guess.
Yeah, it's such a good question. I don't know if what do people I wonder if anybody else we have so many PhD students here in the class. Does anybody have any advice for Jasmine? Any thoughts on how to so you asked a couple questions, but let me ask the tractability question. So like how do you get a sense for whether yeah, Natalie, I love your answers.
Thank you.
Me too.
Thank you, thank you. So, you ask how to quantify beauty, and it reminds me one of the research projects that I was involved in 2021, that we tried to generate automatically humor. And how can we quantify if something is funny? And we actually have a challenge with this, and especially in our field that expects to have a ground truth.
Mm.
And in humor, there is no ground truth.
Oh, there's some things that are not funny.
Yes, you're right. Actually, we use the not funny, the clearly not funny to track that human that did not do their work. Yes, but it was challenging. This is part of the research question, how to evaluate things that are ambiguous.
Yeah. Yeah, sometimes that's the core of the research. Aruna, did you have a thing to add here?
Yeah, I was thinking about how this probably seems intractable because I think in STEM and in ML research, like quantitative evaluations are valued so much.
Yeah.
And like some of these are just qualitative, like what is humor or what is beauty. And
Right.
I think the way that people generally evaluate it is calibrating it with what humans think is beautiful or what humans think is funny.
Right.
And like seeing if you can if you can say use like a language model or something to give you a quantitative score, like say along a scale or something instead of like a binary choice, and then like actually calibrating it with a qualitative evaluation that humans do and seeing if you can calibrate.
This is such a good question, and I really like this calibration question. You know what, I'm gonna, in a couple classes, I'm gonna try to put in some material where we talk a little bit about LLM evaluations and things like that, because I think it's so relevant. And we have a few social science PhDs in the room and who wrestle with these questions of human evaluation every day. And so in your project groups, I'd encourage you to, talk with people and things. And we can talk more about these kind of things on Thursday. Is Ichan here? Is it Ichan or?
Yeah,
Yeah, Ichan, yeah.
yeah. My question is like, when we at the very beginning of our research, do we first do a hypothesis, or do we sort of like experiment with a base model first?
Oh, yeah. What comes first in research, the chicken or the egg? Well, so what do they teach you in sixth grade when they teach you the scientific method? What's supposed to come first? The hypothesis is supposed to come first. That's what they teach you, right? You think that's how all science is done? You start with a hypothesis, and then no, look at all these shaking heads, all these battle scarred PhD students say, oh, if we stuck with that same hypothesis that we had on our first day of starting the PhD, we'd be nowhere. Yeah, it's like this iterative process, right? And so actually, I think that's a little bit of the theme of what we'll do for these first few weeks is give you some tools for this iterative process. I like this question a lot. So I feel like, especially the early phase of research, but actually you can all back up and look at all the research that we do. It's this iterative process where we incrementally ask questions and then we collect a little bit of incremental evidence about those questions. Then it leads us to ask better questions next. And then those better questions are more answerable. And then that might give us insight that leads us to ask better questions. And so at the beginning, we know nothing. And that's actually sort of where we are in our current field, where we have these amazing AI systems. We know almost nothing about how they work. And so we are asking very, very basic questions about them. We have very, very rudimentary methods. So I have to apologize for our very rudimentary methods. So I'm going to start teaching you some of the rudimentary methods. If you take this class again in 10 years, I'm sure there'll be much more sophisticated methods, but we'll do what we can. And so I think that the tool here is an exploratory experiment. You say, hey, is this like I have some interesting question. Humor. I want to know if my AI is, has a sense of humor, right? Does it really, or is it just regurgitating jokes that it read on the internet? Or does it really have a sense of humor? What does that mean? That's one, I think that's an interesting question. Maybe I would teach that in a class. Okay, great. But I'm not ready to do scaled up experiments yet. I have to ask if it's feasible, right? And then I don't really know if it's feasible. Maybe I have some idea of like something. Maybe I'll do a little exploratory experiment. And then I'll take a look around and see how that a really small scale experiment, how'd that work out? And look at the results. Oh, were the results interesting? Am I asking the right interesting question? Oh yeah, if things are looking good, then I take the off ramp and I say, okay, well, maybe time to scale up my experiments. Be serious about this one. But if not, then I adjust my question. I might say, well, maybe there's a more feasible way of asking the question. I loop around. And that's the phase that you guys are in. So right now I'm forcing you as this homework to write down what you think is an interesting question. But then next week, the week after, I'll ask you to do a little bit of exploratory experiments and then maybe adjust your question accordingly. And then we'll go around the cycle a little bit until you feel like you have things that you can scale up. And then we'll talk about methods you can use to scale up your experiments. That make sense? Okay, so today we will talk about, oh, wrong computer. Well, oh, we'll talk about the exploratory experiments. Talk about an exploratory experiment method. So, okay, here's my goals for today. So, I'm gonna try to cover 4 things in the time that we have. Who here knows what a neural network is? Okay, who here is not quite 100% sure? Okay, everybody's pretty good. A few, 1 or 2, right? I'm gonna give you a whirlwind review of neural networks, just in like 4 slides, right? So that we're all talking the same language and give you guys an opportunity to ask specific questions, get us all on the same page. Neural nets, like transformers. And then I'm gonna go from that straight into the first interpretability method, the logit lens. You guys had a lot of questions about the various papers that we had, so we'll stop and we'll talk along the way. And then hopefully we have a good half of the class to do some hands-on setup. We'll like run through some notebooks and we'll look at some experiment reproductions that you can do with the setup that we have. Okay, sound good? Ready? Here we go. What's a neural network? It's an old idea. This is a picture from Frank Rosenblatt's 1958 perceptron paper. It's still how we do it. Still how we do it today. It's the same. There are some inputs. These are numbers. This is like a vector of like 1,000 numbers or something like this. Inputs will say X for input. People use these conventional letters a lot when they're talking about neural networks. Maybe you have some interior neurons that like process those somehow, and they produce some numbers, some other vector of numbers you call Z, and then like maybe you have to describe like the process of how you get from here to there, and that process from how you get from here to there is those are the parameters of your model of your neural network. So these are weights in a modern neural network, in a perceptron style network. These neurons are just weighted sums of these inputs. These numbers are just weighted sums mediated by some nonlinearity. Like the simple nonlinearity would be like drop all the negatives, turn them, clamp them to 0. Right, so this sigma is like the nonlinearity. You could have a few different nonlinearities that you use, but this is the common one. So this is the typical setup. This is called the perceptron setup. It was invented by Frank Rosenblatt, or it was invented by some folks that came before Rosenblatt, but he was the first one to implement it in a physical system, and it works. So actually, the way it works is you like have these things, take linear combinations of those things and clamp the negatives, and then you'll stack it up with another layer of neurons. So like here's another layer of neurons, Y, And we have parameters that describe how to take linear combinations of Z to make Y. And we do the same thing, and we can stack them up as much as we want. If you stack it up deeper than about 3, then then Jeff Hinton will say that you're using a deep neural network, which sounds like deep thought, and it's a very good marketing term. And it also happens to be deeper than 2. But the interesting thing is that even if it's deep, you can train these systems by gradually adjusting the weights to match examples by reducing error. And so that whole process, gradient descent, take all the classic machine learning classes on doing this. We're not going to do that in this class today. But there's a very straightforward training procedure that tends to work if you apply the right tricks. And sometimes we'll take this, I don't know what happened to my fonts here. We'll take this whole, details, and we'll just abstract that. And we'll say, hey, Z is just a function of X mediated by its parameters, right? And then Y is just a function of Z, just mediated by its parameters. And the reason that we will write that is because in 1989, Cybenko proved that if you have 2 layers of Rosenblatt-style perceptrons or deeper, then it's what's called a universal function approximator. If the middle layer has enough neurons, then you can get arbitrarily close to any function. Like Y can be any function of X with the appropriate settings of the parameters if you have enough middle neurons. So like any function that you can imagine, any function in the universe pretty much, right? You can express as a neural network. So that's why we're stuck with this funny old 1958 architecture, because it has this power. And this is also why some people will just write a neural network as F, because they just drop it in as a universal function approximator. Make sense? Okay, so that's the background. So that's about 4 weeks of neural networks in a slide. Okay. So then, and then when you have 2 layers or more, then we call that an MLP. Actually, 2 layers is enough, says Cybenko. You often see MLPs which are just 2 layers, but multi-layer is the general thing of what people say. So whenever you see MLP, that means you've got like a 2-layer thing of neural networks. Okay. All right, and that means you have an arbitrary function there that's learnable. All right, so second thing to review is, what the heck is a language model? Okay, so a language model is it's a way of modeling language, I guess. So let's see. I'll just sort of skip to the modern formulation of what people use for a language model and say, if you have a language model, what you really have is you have a function that tells you what the probability of the next word is going to be. That makes sense? Now, that probability is not unconditional. I can't just tell you that V is the most common word, and the probability you're going to say V is like 2% or something like that, because that's not interesting. It's a contextual probability. Like, I'll tell you that you'll say V, or you'll say hyphen or something like that, with a certain probability conditioned on what came before. And so a language model conditions its probability prediction on all the words that you said before. So that's what a language model is. So that's like physically, that's what it is. It's a function that tells you what the probabilities are of the next word, given the context of where you are in the text. That makes sense? And people have used language models for a long time for all sorts of things. People traditionally use language models to like smooth out computer-generated text to make it more fluent. They say, if you want text to be a little bit more fluent, then you should match the statistics of text, and they use these as statistical modelers. And the big surprise over the last few years has been that these language models are not just like statistical smoothers that make like language more fluent, but these are the things that are like getting up and talking and thinking and like programming for us and stuff like this. It's very weird. So the focus of our class is going to be these large scale language models, which have very, very good models of language and behavior, but they all have this form. Given some context, give me some probabilities. So there's a couple details here. The context is always provided the naive way to think of it is the context is provided in words, and the output is provided in probabilities of the next word. That's what you'll say to all the lay people. Of course, the detail is it's not words, strictly speaking, it's tokens. So there's a process called tokenization. See the self-referential example here. There's a process called tokenization. And the way it works is if you have a really uncommon word like tokenization, it might be broken up into littler pieces. So here is like a process called token, and you feed that to the language model, and it'll tell you that 99% of the time, or whatever, 90% of the time, what you really need to say next is isation, the second half of the word as the next token. But then there's some other things like tokenizing, maybe that's sort of 9% chance you might say that. And then maybe there's a hyphen, the sort of 1% chance you say a hyphen or something like that. And so this is sort of how the language modeling goes. And so what you're doing when you run the language model is, oh, wrong computer, is you're making a prediction for what you think is going to come next. You're never 100% sure, so it's always a probability distribution. And then if you actually want to talk to this language model, if you want to do some dialogue, then you have to do sampling to actually follow through on that prediction. Pick one of the next words, say this is, if the language model were speaking, it would say isation, because I guess 90% chance, right? Or you could roll a dice and maybe 10% of the time you say it is ising or something like that. So there's different sampling methods. And then after you sample, you just take the token, you just jam it into the context, and then you run it again. And then there's this iterative process where you just keep on running the language model over and over. And then it just generates this beautiful fluent text and has a dialogue with you. And then, does your computer programming for you or whatever. Isn't that crazy? It's crazy. It's crazy that this works at all. But that's what a language model is. Any questions? Oh, yes, actually, Ayush had a question about language models. I forgot what the question was. Is Ayush here? Yes, Ayush, what was your question?
He was on this,
Yes.
and currently like might be on past level, but
Yes.
definitely there must be something that's going on by tokenizing, let's say, object centric or like seeing that implementation.
Yes, 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 yes. So this whole idea of tokenizing text came from the text arena. Like, what the text modelers really wanted to do is they wanted to have one word per input, except that words are so weird, people misspell words, and there's very obscure words, and there's little phrases like that maybe you should treat the whole phrase as a word, and there's all sorts of weird situations. So that's when they said, okay, you know what? We're not going to stick to words, we're going to introduce tokens. Tokens are going to be some chunking of text that is just like statistically useful, and we'll use tokens instead of words. And then after they introduced that, then people coming up and wanting to use this class of models on other types of data, like images or sound or physical experiences or things like that, they said, how do we, these language models are working so well for the NLP people. Can we use these things on other types of data? And the answer is yes, absolutely. You can break up images into tokens, right? You can break up physical data into tokens. You can break up biological data into tokens. There's different ways of doing it. Like you could represent graphs as tokens. You can represent other things as tokens. You can quantize image data in a bunch of different ways, or you can have continuous tokens that aren't even quantized, things like that. So there's a lot of different techniques. I'm not going to go into them. But the general idea is that at least with current neural network architectures, there's some overhead for processing like a token. And so you want the tokens to be chunky enough that when you spend all that electricity to process one token, you make some appreciable like progress in your computation. So if you make the tokens too small, it tends to use too much electricity. If you make the tokens too big, it causes other problems because they're too coarse to capture the details. And so there's some trade-off of like how you tokenize things. And so the image people probably debate a lot about how big a token should be. Should it represent a little patch of an image or a big patch of an image, or how should we do it? But we won't get into those things. You take a regular machine learning class on computer vision to see those debates. That make sense? So in this class, we'll focus on language. Some of the tokens will be approximately a word, sometimes a little more chunky, sometimes less chunky than a word. Make sense? Okay. So next thing. All right, so that's a general language model. That's a general neural network. And so what is everybody using now? They're using these transformers. So who here is very familiar with like what a transformer is? Okay, great. And who's like could use a refresher? Okay, a few people. So we're covering this. All right. So this is what the neural network architecture of a transformer looks like. The input comes in on the left, and the output comes out on the right. It is a language model. So the input is all these tokens for the context, for all the words that came before. And the output, even though I wrote this as a single word output, it's actually, the output is this probability distribution telling you what the likelihood is of all the next tokens is going to be. That makes sense? And so it has three phases, right? First, to have a neural network, you need neurons. And so the neurons all have to be set to numbers. It's a numerical network. So these tokens are no good. So you need to encode them. So basically you take every token and you turn it into a vector of numbers for all like the neural inputs that are going to be provided on the input side. So Miles, Davis, each one of these things turns into a whole bunch of numbers, about 1,000 numbers. So there's like 1,000 numbers that correspond to Miles. And there's a different 1,000 numbers that correspond to Davis, and so on, right? And then each of those numbers gets fed into the input of the neural network. So the how do you get those numbers? It's called the encoder layer. It's literally a lookup table. There's a vocabulary of something like 50,000 or 100,000 tokens, depending on what vocabulary you're using for your neural network. And the encoder is just a list of 50,000 vectors of 1,000 numbers. It's like a big matrix of 50,000 by 1,000, where you just say, oh, Davis is the 300th line in the vocabulary. I'll go look at the 300th line of this big dictionary, this matrix, and that tells me what 1,000 numbers to write down. I light up these 1,000 numbers in that form, and then that gets the network started. That makes sense. So that's the first phase, is we do that, and then there's a series of neural network layers that are it's very deep. It's like hundreds of layers deep, not just two, but there's many neural network layers that take these inputs and they mix them in some clever ways, which I'll talk about in a minute, right? That transform all these vectors all the way out to a similar. So if you had 4 vectors, each corresponding to a token coming in, then you have the same number of neuron outputs on the output side of a transformer. So a transformer is rectangular. It takes an arbitrary number of tokens on the input, and then it outputs like the same number of vector outputs on the output side. So each one of these little purple dots represents a vector of about 1,000 neurons, 1,000 numbers. That makes sense? So I'll talk about this internal architecture in a minute, but it just does all this stuff. After it goes through several rounds of this computation, you get to the end, and then you decode it back out into tokens again. So you have this 1,000 numbers, and then it goes through a little neural network layer that turns these 1,000 numbers into 50,000 probabilities of what the probabilities for each possible next token is. And that's just another matrix, just a linear operation to do that. But then we use a softmax to make sure that all the output numbers add up to 1. But it's just an output layer. Okay, so that's the overall, it's like just 3 phases. That's what a transformer is. I'll talk about a couple of things, details in a minute. Any questions at this stage? Oh, how you, he, and Ananya, how you? Yes.
Yeah, so my question is, so at the encoder, so we convert a vocabulary to embedding.
Yes.
And we have some sort of operation, have a very meaningful representation.
Yes.
And
Yes.
just refer back to the token for the next step generation.
Yes.
So my question is, can we just leverage that embedding? I mean, without converting to token, just
Yes.
use that as a embedding for the next, for the next word.
So let's see. There's some like I think the adapting from the token vocabulary to the embedding. I'm not sure if this answers your question. So ask again if I'm not quite hitting it. But some of these numbers are adjusted to make them line up with what worked well in practice. So, what ends up working well in practice is token vocabulary somewhere around 100,000. So there's a couple thousand words in English that are commonly used words in everyday speech, but then there's a lot of languages to handle, and there's a lot of technical text and a lot of other things. And so people for a long time used token vocabularies around 50,000, right? To capture a lot of this subtlety. And then they realized, oh, actually, they can get better performance out of the network if they go up to about 100,000, 150,000 token vocabulary. So you'll see this pretty large token vocabularies, but the natural way to represent a 50,000 way choice in a neural network is to have 50,000 neurons, all of them off, except for the one that's your choice. So that we call that a one-hot encoding, with all the neurons off except for the one thing. But it turns out that's kind of inefficient for neural networks. It's not dense enough as a computation. It wastes a lot of electricity to do that. Like the widest that a neural network seems to perform with modern hardware and modern architectures is around 1,000, something like 1,000 or 5,000 or 10,000 neurons wide, one of these representations. So you'll see it's pretty frequent to have 1,000 or 10,000 neurons working as a bank, as a vector, as a neural representation, instead of like 50,000 or 100,000. So one way of thinking of what an encoder is doing is it's taking one numeracy, like the number that people thought was like a good engineering number on one side, the vocabulary side is about 100,000, and it's reducing it down to some other numeracy where some other engineers are saying, oh, no, this is about the right dimensionality for this other problem, which is like 10,000. So like this tenfold decrease in size means that we're taking this pretty large vocabulary and we're like compacting it down to vector choices in a smaller dimensional space. 10,000 dimensions is still a lot. But I don't know, did that sort of answer your question? Not really.
So I mean, at the final.
Yes. Yes, right.
Yeah, we have an embedding.
Yeah, so it's like 10,000 numbers or 1,000 numbers. Let's say it's 1,000. There's like 1,000 numbers here.
So can we just use it as for the generating next word?
Oh, can you generate a next word straight from this 1,000?
No, I mean for the next.
Oh, like could you take this 1,000
Yeah.
and then just feed it in here
Without
for the thing? Yeah. Could you do that? Yeah, I don't know. I think that there's something. I think it's a good question. It's a good question. So if you do that, you're not making any choices for the network. You're not like collapsing its probability distribution down to a choice. You're just saying, hey, you know what? I'll take this blurry probability distribution you have, and I'll just take this blur thing and I'll just feed it in as input for the next thing. Now, obviously, the network's not trained to do that. So physically, you can't do that. But you could conceivably try to train a network to do that. Why don't we do that? My guess is that there's something special about actually the sampling procedure, about actually forcing the network to make a choice. Says, oh, these two things are equally likely. Well, like we need some way of encoding the fact that in the real world, you're going to do one of those things. You can't continue to think about both of those things on an equal basis forever. You've got to sort of make an observation of the thing that you're going to actually do. You're going to have to utter this word and make a choice and then go on. And so I think that I think that's actually important for these language models to work well. But I think it's a really reasonable question, and you could do research to prove me wrong. Right? Yes.
Yeah, I'm not a social scientist, so I apologize for very.
Sure. Yeah, it's okay.
People talk about a decoder transformer.
Yes.
What's that referring to?
This is the decoder only transformer. So okay, so there's all right. So historically, the way that transformers were invented, there was a Vaswani paper called "Attention is All You Need." Who is familiar with that paper title? Oh my gosh, what a paper title! Attention is all you need. I don't know. But then they had several things in that paper. So they said that this general architecture, they set it up in two ways. They set it up as an encoder architecture, and they also set it up as a decoder only architecture. So let me see if I can digest what the difference is for you really briefly. So the idea is that the encoder's job is just to read text. It doesn't need to write text. So it never predicts the next word. It just tells you what the words that you have mean. And the way that you set up a transformer, if it was set up as an encoder, is that this little vector, which captures some meaning of like what this word means, by the time you get to the end, this vector still is talking about that same word, right? Except that it has a lot more context. And so by the time you get to the end, these vectors that you get to the end have a really meaningful representation of what that word means in context and what the whole context means and everything, right? And what do you use those vectors for? Well, you could use them for a lot of other things. You could use them for classifier or for drawing an image or something like that. Like so, like if you want to draw a picture from a piece of text, it would be very reasonable to take a text encoder and then take the output of the text encoder and feed that into an image generator, and the image generator would understand all the subtleties of language that you used to generate its image, right? So that's what an encoder architecture is, but it doesn't need to speak. It doesn't need to generate text. What a decoder architecture is it shifts that role by one and changes the job. So decoder architecture is very weird because even though this is representing the word the at the beginning, by the time you get to the end, what this job is, what the network is trained to do is trained to tell you what it thinks the next word is going to be. So, the next word, it belongs down here, strictly speaking, right? The representation of the next word would be sort of the next neural line, except that if you have to speak, if you have to be a language model and predict the next word, you can't input the next word over here and have a line here, right? Right. So what they do is they just shift all the roles by one. And they say, if you inputted one word, then your job is on that neural line to predict the next word. Does that make sense? And so this shifted thing where you don't get to see the future, right, is called an output only transformer. And so you have these encoder transformers that can only read, and you have these output transformers that aren't really designed to read. Of course, one of the secrets is they do read. They read themselves. They read their former past, but they're completely trained to say the next thing. That's their job, right? And in the original Vaswani paper, they had this funny hybrid architecture where half of the neural network was an encoder that only read text, and then half of the neural network was a decoder that only uttered text and ran. This is called autoregressively. After you pick a word, then you feed it back into the input, and then you run it again to like get the next word. So this loop is called the autoregressive loop, and so they had this reader and this writer, and they said when we set up a reader to read French, and we set up a writer to write English, and we hook them up in a certain way, then we can get better natural language translation results than have ever been achieved in history. Therefore, attention is all you need. Mic drop, right? And why was that such a moment? It's because natural language translation is one of the oldest problems in computer science. A lot of the original funding for computer science in the 1950s and the 1960s came from military sources where they're like, I think that World War II would have worked out a lot better if we could read German or Japanese better. We should have computerized natural language translation systems, and people like made these things, and none of them worked very well. It's been this holy grail for decades. And then we all live in a world where there's been Google Translate for a while, which has been considered this amazing, engineering triumph. But actually, These attention is all you need transformers outperformed everything that the statistical machine language translation people did by quite a big margin. And so that's why like they invented the thing. Little did they know this architecture would take over the entire field and sort of encapsulate like basically every cognitive task that we set in front of them. That makes sense? Okay, so that's the answer. And the other historical note is that Google invented this encoder decoder architecture that was from their paper. So they had a lot of encoders. They actually said, hey, for a search engine, which is all about reading the internet, we just need encoder only architecture. So they threw away the part that speaks, and they only used the encoders to go index the internet. And they tried to get everybody to study these and make them better. And they got a lot of academics excited about making these systems like BERT or whatever, right? That they're encoder only things. They're read only neural networks. And then the OpenAI folks were like, no, we want to like pass the Turing test. We want you to have a dialogue with our system. We wanted to talk. And so Alex Radford and folks over there said, we're going to make the opposite choice. We're going to throw away the encoder and we will just focus on getting the engineering working for a decoder only thing that can speak without focusing on the reading part. Right? That makes sense. So that's the historical note. So there was this split between these two AI labs of what their focus was. And the OpenAI guys made these the really large decoder only systems. And that's how they released ChatGPT. And then ever since then, people are like, you know what? We don't need these encoder things. The decoder things can also read. They read themselves. Yes, go ahead. Yes. Yes, that's right.
Curious if most of the techniques covered in this class are agnostic to whether it's encoder, decoder, or they more focused.
So like some of them, there's a mix. Some of them will be the work on both, and some of them are really very focused on the decoder architecture. So there's a funny thing, which is, I suspect that there are certain aspects of the decoder only architectures which are more amenable to interpretation than the encoder architectures. Decoder architectures are forced to do something which humans have to do all the time. They are forced to make decisions constantly. So this thing that I was trying to make a big deal about, like, there's going to be a sampling thing. You output this distribution, and then at that moment, like, the sampler is going to make a choice. It's going to say that you chose this word. You're going to say trumpet. There might be another word that you could have said. You could have said horn, but you're not allowed to think about both these things at once. You're going to say one of them, and then you're going to, put that back auto-aggressively, and you're going to continue. So this constant making of choices, this bottleneck moment of the present, where you're going to do one thing in the future, is this thing that the autoaggressive output only neural networks are forced to do, and it feels like, my intuition is it feels very human-like. It's just like the choices that we constantly face as humans of like, what is the next action we're going to take, and as a result, the internal neural pathways inside these autoaggressive, like these speaking output only models, like feels like they're organized in a way that's kind of comprehensible to us. They seem to make decisions. They seem to try to collect together the data. They need to make a decision and make the decision. Whereas encoder only architectures are a lot more diffuse. They never have to make a decision. They're just trying to get this gestalt. And and so it can be harder to get intuition about what they're doing inside when you look inside. That makes sense? So, right. So, but some of the methods will work both ways. But you'll see some methods that are very focused on this. And this is a debate because a lot of people are like, these encoder only architectures, they should be more powerful than the decoder ones. But I don't think that that's been shown to be true. I think people have studied the decoder only architectures and they found that they're incredibly powerful. And there are tricks that you can use. So some of the folks here are in labs where they they train decoder only models on like computer code and things like that, or editing tasks where, when you're editing a document, you don't edit things always at the end, you might edit things in the middle, but there's ways of getting the autoaggressive architecture to work on things out of order. think of the way that you work with an editor, like a word processor. Like you'll scroll up and you move the mouse and you click on things. You have like this forward in time sequence of things that you do. You can train an autoregressive model to do these types of things, and arguably it might even be smarter than one of these encoder models. Make sense? Okay. So, oh, that's pretty deep. How about Ananya? Did you have a question?
Yeah, hi, I'm actually online.
Hi, nice to see you.
Hi. Yeah, I had a question. I guess I was having a difficult time forming an intuition why like features encoded within the representation spaces may be linearly separable. Um,
Yes.
I would
Cool.
imagine like, yeah, sorry.
Yes. Um, so you're asking a question that is, has puzzled machine learning scientists for a while. Like, what makes a deep neural network effective? When you make it deeper, what's the benefit of depth? And um, and so I'm not going to give you a total answer, but the intuition is that um, it's sort of like it organizes information better and better the deeper you go, and it represents better and better useful abstractions. So at the very shallow layers, you have a word like plays that is just it can only be represented as the word plays. Like the first token that comes out, the first vector that comes out of the word plays here, just means that the word plays appeared in the text. But we have no idea if that's a verb or a noun or in one is it an instrument is being played, which is what it means here, or is it a child who's playing? Is it an act, a stage act, a play, right? There's so many different ways that like the word play could be represented, and in the very first layer, there's no linear separability. There's no way of looking at that vector and telling which meaning you're talking about, right? There's no like if you try to separate childhood concepts from adult concepts or something, like you can't separate plays at that layer. But as you go deeper into the network, then you might be able to separate all the childhood concepts from all the adult concepts, even though plays is this hominin. It's both. But by the time you get deeper into the network, it may have separated those two types of meaning into two different parts of the vector space. So that's a little bit of the intuition. But there's a lot of deeper theory that goes to that. Does that help at all?
Kind of, yeah. I think it helps in understanding. I do have other questions, but I can definitely like if you have any links to read up on this.
Okay, I'm
And
gonna keep on going.
yeah,
Okay,
thank
we're
you.
gonna we're gonna forge ahead. There's much to talk about. One of the funny things about transformers is because of the way they're trained, when you're using them autoregressively as a language model, you just need to know the probability distribution that's coming out of this last thing. But because they're trained in parallel, you actually get a probability distribution like at every single token. So even though it's like if you say miles, then it says, oh, you know what? I think that the next word is per, like miles per gallon, I guess, right? Even though the next word, it knows the next word is Davis because you just fed it, right? But like, this neuron doesn't get to see what the next word is. It was forced to make the guess for what comes next, and you can read these guesses out. It's a little bit funny. You can see how the evolution of all, of its incremental predictions are going. And all the transformers now, they all do this today, all these autoregressive things. And that's why people had this intuition that, oh, it's really wasteful. Like, why am I making all these irrelevant, predictions that I don't need to make? Like, I'm wasting all these neurons on doing this. It must not be as good as like an encoder only model that doesn't do this type of stuff. Um, but I don't think that the science backs this up. I think the science has, uh, been quite happy with these decoder only models. They perform very well, maybe even better than the encoder ones, even though they're doing this weird, useless thing. Okay, so um, important transformer pieces to know. We talked about the encoder, we talked about the decoder, and then there's two main other pieces. There's attention, which is all you need, they say, right? And what it is, it's a kind of neural network architecture. It's like a way of hooking up neurons that remembers recent information from other tokens, right? So it's these red lines that reach back to previous tokens in the context. And there's all this detail of how attention works. It makes this query vector, matches key vectors, and then uses the query key matches to recognize which previous tokens were the most important, and then it gathers vector contributions from those most important ones together, and then brings all that information forward to now. So that's what attention is. If people are interested, we can talk about that more. And then MLP is what this is Frank Rosenblatt's architecture. It's just two-layer neural networks that match and modify single token feature vectors. They just have some input neurons. They put them through some neural network magic to get a universal function approximator. And then they output something to add into the vector. So attention, it turns out, is not all you need. You also need MLPs, right? There are actually more MLP neurons and weights in a transformer than there are attentions. So it was a lie. I'm sorry. You need MLPs also. And then other than that, though, there's very little. You have encoders and decoders. There's some normalization layers that just keep everything from exploding. Keep everything normalized to about size 1. And that's it. That's pretty much it inside a transformer. And so there's another trick so I guess the way I think of it is, I think of attention as, look, I put this little thing there that's not quite science, so it's diagonal. I think of attention as the implementation of short-term memory in these things. So if you go to a person and you say, what kind of memory did I just talk about? You would say short-term memory. And then how do you remember that I said something about short-term memory just a second ago? Is it because you rewired, when I said short-term memory, did you rewire your neurons inside your brain to like store this memory that I said short-term memory just a second ago so that you could regurgitate this when I ask you what kind of memory am I talking about? I doubt it. There's actually a lot of neuroscientists who have been going around peddling this idea that, yeah, as soon as I utter short-term memory, that the neurons are instantly wiring themselves up so that you remember this. This is how short-term memory works. I don't believe it at all. I think short-term memory is just transient electrical signals that are circulating around in your brain that you can regurgitate and remember something without having to make new neural connections. And that's what attention is. Attention is a way of remembering what happened recently by looking at the context from all of the neural activations, from all of these numbers floating around without rewiring permanently the architecture of the computer. Now, the reason attention works so well is that because it sort of has this temporary rewiring that does this query key business where it says, hey, I'm going to only pay attention to certain neurons that are the most relevant, whatever, right? It's sort of a way of it sort of pretending that it has a neural connection over there just for a moment. Like I'm going to run a query and then listen to specific neurons. But that's not a permanent connection. Like that goes away as soon as the context changes. And so I think of attention as short-term memory, and then I think of MLP as long-term memory. There's a lot of parameters. The bulk of parameters, most of the parameters in a transformer are in MLP layers. And where do these parameters come from? These weights and these biases, they come from all this gradient descent training from, like you're exposed to all this data and you try to match it. And then most of that data turns into encodings of weights in these MLPs. And so when you remember something like the Eiffel Towers in Paris, it's not because it was mentioned recently. It's because you remembered this association of Eiffel Tower in Paris and then stored in an MLP somewhere. That makes sense. So I think of MLP as long-term memory. All right, not very scientific. Some neuroscientist is going to kill me. Okay, so, but that's the way I think of it. Okay. Yeah, so I won't talk about the details of self-attention, but we do have a question from Lucy, which is why I put this slide here. Is Luz or Lucy here? No. Okay, that's okay. Maybe somebody came in the first class and not here. That's all right. So there's just a question about how attention works, and I was going to use this slide to answer it. But that's all right. But if you want to know more about attention, there's lots of YouTube videos and things like that. So I encourage you to read them or watch them. There's a concept that you need to know to understand how logic lens works, which is it's called the residual stream. So it's a very clever way of hooking up deep neural networks. So instead of taking X to Y to Z, you know, whatever, right? And then taking the output of one neural network layer and then making that the input of the next neural network layer and then just stacking them like this. What we actually do is we use what's called the residual architecture, which is very weird. So, okay, so in a transformer, you do have layers. Like in the transformers we'll play with in the lab today, there's like 80 layers, right? A lot of layers, right? And each layer has some input, which is like a vector, like for a given token stream, it'll have like a layer input, which is like 1,000 neurons or 10,000, and a layer output, which is the same number of neurons, right? And then there'll be a little attention thing and an MLP thing that go between them. But look at the way that I drew MLP and attention here. They're like to the side. Because what's going on is every layer is not taking this input and then producing this output. Every layer is calculating what's called a small residual vector to add to the stream. Does that make sense? So if I ripped out these neural network components and I just zeroed them all out computationally, then this vector would still pass through to this one and be exactly the same. So that's called the residual stream. So without any special neural network connections, the vectors just remain the same. And so the bias for transformer is for it to gradually transform vectors from layer to layer, you know, sort of slowly, and add little residuals at each layer. And what that means is that if we want to know what the deal with this vector is and how to interpret it, one clue is if we already know how to interpret this vector, it's probably not that different. Like most of like what you need to do to understand this vector is the same as what you have to do to understand this vector, except that these components might have added something. So there's just a little bit of a gap. And so you could try to understand what these components are doing, but they typically will add like less than 10% of like vectorness, vector size or something like that to the vector, right? It's just like gradually changes it from layer to layer. Make sense? So so this is called the residual stream architecture. And it means that it has some interesting implications. So 2016 and in 2020, people looked at these residual network architectures and they realized that there was this cool thing that you could do called early exit decoding. So it takes a lot of electricity to run one of these things and time. And what people notice is that after you go through like 70 layers, you've got 10 more layers to go. You know, when you get to the last layer, you're going to decode this thing. And it's going to be a probability distribution. It's going to say trumpet. But these last bunch of like vectors are pretty similar to each other often. They're pretty similar. So what Panda and Abaya, you know, proposed was maybe we can just skip the last few layers. Maybe like we can guess close enough. Let's like save the electricity. We'll just call an end to this game and we'll just decode right now. So if you skip the last layer and you decode, it often gives you the same prediction. Trumpet. And you could actually skip a few layers and it would keep on giving you the same prediction. Right. And so this is called early exit decoding. And the funny thing is that if you skip too many layers, you'll get like slightly different things. You peel off trumpet and it'll start saying other things like horn. And if you peel off layers, right, you'll start saying other things like Miles or Stein or whatever, right? It's just like say other random things as you peel off more. But this is interesting. So what happened is around 2020, people, a blogger, nostalgiabrist, suggested, hey, we should do this on purpose to get a little insight on what's going on inside the network. And they call this the Logit lens. This is applying early exit decoding to get a little bit of insight about when the model is prepared to make certain predictions. Sometimes earlier and sometimes later, but a little window in the insight. So this is called the Logit lens. So so there's a lot of questions about Logit lens. Is Isaac here? Oh, Isaac, okay, what did you want to ask about Logit lens?
Yeah, so in the blog post, the author suggested that, early on in the model, they right outcome.
Yes.
And then in the, other piece about the internal language, it suggested that actually it's still working on.
Yeah.
What-
Yeah. Yeah.
What to, uh, guess the output control.
Yeah.
So I was wondering about, if I'm understanding correctly, and then if so.
Yeah, I think you're understanding it correctly. So basically, the story is that because of this residual architecture, the models frequently, especially the shallower ones, like GPT-2 is a smaller model. It's a little less true when you get to the very deep ones that have like 80 layers, like Llama that we'll see. But even at the early layers, especially for the smaller ones, it's already prepared to kind of guess what the next word is going to be. Um, and you get what language model people call bigram statistics. Like what is like without knowledge of any context, like what's the next word that comes after miles, right? Without any context, the next word is going to be per, like miles per gallon, something like that. And and so so if you go back to really early layers of like GPT-2 and you decode what do you want to say now right after miles at like layer one, layer two, it'll probably say some word like per. It like already knows. It already knows like what its baseline guess is. Um, so it'll know that very early, but then as you get later in the network, um, it absorbs more of the contextual information and it'll change its guess and it'll have a more sophisticated guess later on. And so both of these viewpoints are, I think, correct. That especially in smaller networks, the early layers do mean like what an initial guess would be. Um, when the networks get really big, when you get like 80 layer networks, then it's less clear what the role of the early layers is. You can kind of think of it as like, yeah, the networks kind of know that they have a lot of time before they're going to have to make a decision. And maybe even making that first guess is like a waste. Like, why guess now? I don't have to give you bigram statistics now. I should like do some other computation for a while. I've got like another 50 layers before I'm going to start running out of time. And so what are they doing in this mysterious interior 50 layers? Well, we're not sure. That's what a lot of the research is going to be about. But still, we can look at it with Logic Lens anyway and see, but it might be a little less meaningful. Okay. So, and then Avery had a question. Is Avery here?
Yeah, it's kind of like mentioning, is it appropriate to kind of apply the load lens to earlier layers, especially for transformers when it's not really,
Yeah.
coming up with real,
Yeah.
well, guesses, it's time to use it later thinking.
Yeah. It's probably not that appropriate. It's okay. I mean, it's a thing. You can just do it, but it comes with this caveat that it might not correlate with any real prediction. It might not be that meaningful. There's a series of papers that I think that I linked somewhere in the reading on the website called like tuned lens and other types of lenses. So like there's variations on Logit lens that try to correct for this. So they say, hey, you know what? When you get to the early layers, the thing to do is not to decode them directly. But there's like an average transformation that the early layers tend to go through by the time they get to the end. And you can learn what that average transformation is. And if you just apply that, then that can give you more accurate decoding of what's going on. So that's the tuned lens idea. And then there's other things. I don't know if Sheridan is on the West Coast. Otherwise, I'd have Sheridan give a lecture about the concept lens. Maybe I'll give that talk at some point. But there's other ways of decoding earlier layers. Okay, so, but yeah, but Logit lens is the most straightforward thing to do, and it might not be totally valid, but I'll point you to other research to look for that is like different nouns before the word lens. Tuned lens, contact lens, future lens, attribute lens. There's a bunch of people who've like come up with different lenses. Make sense? Okay. All right. And so we're going to do this UI thing. What I'm going to ask you to do in a minute, and you can do this now if you want, is if you go to workbench.ndif.us, then you can actually play with Logit Lens, and I'll step you through an example experiment to do with Logit Lens right now. So this is the Logit Lens grid. and it lets you view like a transformer grid as next token predictions. It's just like, that big grid that we had, if you just go to any one of these purple dots and you stick the transformer decoder on it, this is what the number one token prediction would have been at that point. And so I guess this is Miles Davis plays and if you just go to like layer 30 and you stick this thing on like a little bit early, then it says horn, right? And so you can see that before it was going to say trumpet, it was going to say horn. And then before it was going to say horn, it was going to say Miles. And before that, it was going to say Stein. And before that, it was going to say some other things. And then it has some CSS or something like that. It's going to say, I don't know what, right? But it has all this other stuff that you're going to say, right? And so you can kind of do this. And so, okay, so that's what this Logit Lens grid looks like. And then there's a few questions about Logit Lens. So is Eunice here? Yes, Eunice, what was your question?
So, the paper kind of differentiates the layers, cluster layers into two groups, input, concept, output.
Yes.
And what they label the middle layers as concept layer looks to me kind of it's just labeling to unidentified phenomena.
Yeah.
Just so assertive say that this is a conceptualization.
Yeah.
As a social scientist, I kind of hard to understand how they label it as a concept.
Yeah. Yeah. Like how come they're so assertive about this? Yes, I agree. It's like the circular thing. It's like, how do you know what's the reality of what you're seeing in Logit Lens? I think that you're right. Logit Lens is a funny way of looking at things. It's this accidental view that we have, and it's not clear what the insight is that you give. And I feel like when different people write about the early layers tend to give you insights about the input, the final layers tend to give you insights about the output, and the middle layers tend to give you insights about like the abstract concepts. This sort of assertion is very qualitative. A lot of these assertions are not backed up by quantitative experiments yet, although some people attempt to do this, but there's a couple papers maybe I can point you to that try to quantify these things. But the science is not very locked down yet. But there definitely are patterns, and people are writing in this maybe overly assertive way to share the qualitative experience of what they're seeing. And so I think that's a real state of what's going on. Yeah, and it's how people are not being maybe careful enough in the words.
None of them are social scientists, so
yeah, they're not social scientists. They're computer scientists waiting. And actually, so computer science is almost a misnomer. Computer scientists, we're in this very weird position where we're all trained as mathematicians and engineers. None of us are trained as scientists. And so as a field, we tend to not be very careful writers. We say this is how it is because we're used to engineering systems. And when we make assertions about systems that we've engineered, we can speak confidently because we put that into the system. And that's how we write. We're in a very weird situation with these neural networks where we didn't put it in. So we should be more cautious about what we say about these things, but the sort of the culture and the style of the field is, maybe not adjusted to that yet. So that's the way I'll apologize for the computer scientists. And say it's just sort of the way that we write. So yes, but I like the question a lot. I agree with you. A lot of the writing is a little bit over assertive. But on the other hand, if you don't write over assertive, like it can also be hard to communicate to other computer scientists. It's hard. So we're in this funny period. Claire had a question. There's maybe a similar question. Is Claire? Who's Claire? Oh yes, Claire.
Oh, I thought that maybe the way we're doing this is like irrational.
Yeah.
We're saying that the space of which the decoder works on the last layer is the same as it works on every layer, and I don't know if that's true.
Right. That's right. It's definitely not true. At least strictly speaking. So the decoder was only trained to be able to decode the last layer. It was not trained to decode any other layer. So the fact that does anything that's interesting at all at other layers is some weird accident. It wasn't something that was put in there intentionally. But it is a residual network, which does have this mathematical accident that the layers do tend to resemble each other from one layer to the next. So it's not completely unfounded. It's not completely accidental. And I think that the structure might be such that at some point, like careful proofs or careful empirical work, careful reasoning might be able to really reason through what it is that we're doing when we do Logit Lens. So I don't think that it's completely vacuous what we're doing, but I would agree with Eunice that maybe people who use it maybe are a little bit over assertive about what it tells you because we're not quite sure what it means yet. That makes sense? Yeah. So I agree with you, but I push back a little bit. It's not completely vacuous. It's not completely vacuous. There's something going on. Yeah. And so here, I'll give you an analogy. Like psychologists will do this. They'll say, hey, you know what? I want you to like look at some stimulus and I want you to tell me what you see. Oh, but I want to try to get insight on the internals of your brain. So I'm going to use a stopwatch. I'm going to flick the lights on and flick the lights off so that you can't see it after like 100 milliseconds. And then I want you to tell me what you see. Right. So they're trying to like interrupt the computational process that you have inside your brain to just like a really short like period of time. They'll limit your stimulus. They'll like make you utter something early. They'll let you see something for a really short amount of time. And so this is a little bit in that spirit. It's like this is not the normal way that you go around viewing the world. Like you normally have like plenty of time to see the thing. You don't like see things in like 100 millisecond bursts under a strobe light, right? But the neuroscientists, the cognitive scientists believe that that tells you something about the thinking process, and they try to map out the stages of thinking by doing these kinds of experiments, these stopwatch experiments. And this is a little bit the analogy of it. It's not quite an exact analogy, but it's like, hey, you were expecting to have 80 layers of computation to do this, but look, I'm gonna stop you after 70 layers, just a little early, and I'm gonna make you like utter the thing. And then does that give you any insight? Well, I'm not sure. This is not the way that the model's trained to work. It's a little accidental that does anything at all. But yeah, maybe it gives you some insight, right? And it's kind of in that spirit. It's a loose analogy. Does that make sense? Yeah. Yes.
How we don't entirely know like what's going on in the early years, right?
Yes.
And when you look at Logit Lens, or at least like generally what people believe is that the early layers are doing some kind of encoding. So I'm
Yes.
confused, like when you say we don't entirely know what's going, like what other mysteries you think are there?
So maybe I'm underselling it. I'd say that Logit Lens is not a very good tool for understanding what's going on in the early layers. There are other experimental methods that you can use to try to get insights for what's going on in the early layers, and we will study some of those methods. So maybe that makes you feel better? This is not the only method we're going to use. We're going to learn probing. We're going to learn causal mediation analysis. We're going to learn some other tools that we can use to get insight on what the early layers are doing. Yes.
Oh, this might be like a silly question, but like,
Yeah.
do we have to have early layers? Like, could you make them more comparable if you maybe like you could switch the order of the layers during training and maybe they, I don't know, become more generalist?
Yeah. Wow. You're going to invent like the universal transformer architecture.
Oh.
Yeah, that's good. I think that yeah, so I think these are like sort of engineering-ish questions. Can you make it so that the layers are more transportable? So there are funny things. If you swap the orders of layers in a pre-trained transformer, it doesn't damage the capabilities of the transformer that much. It doesn't really notice that much that the layers are moved around. Unless you start swapping layers really far, like the early layers with late layers, then it starts to confuse things. But if you like go to adjacent layers and you mix them up, it doesn't change things too much. So there's some spirit in which like the residual stream is already giving us this ability that to say layers are not that different from each other. Um, but yeah, but people don't train them with that as the goal. Right. Early layers are allowed to be very different from late layers. And for the earliest layers and late layers, they tend to be different. So, and then Guangyan had a question about thinking, yes.
Question.
Okay, another question, yes.
So, I was reading about Logic Lens and I was just wondering if it has anything to do with the dimensions. So I think most of the representations inside the model are in one dimension.
Yes.
So would it be possible that
Most of the representations are in like 1,000 dimensions, not one. Say again.
so could it be possible that these representations are like more complex and we need to like interpret them in like in more dimensions or something?
Okay. Um, so the decoder definitely doesn't reveal everything about the representation. So there's like, is Eric in the room? Eric Todd? Yeah, Eric did this nice experiment in his paper where he asked the question, he had found some representations that we'll talk about in a few weeks inside the neural networks, which don't really seem to correspond to words very well. And then the question is, if you try to, so what is in those 1,000 neurons if it's not like a word prediction, right? So the thing about this logic lens thing is you can think about a lot of thinking in a neural network, especially as a language model neural network, as like achieving the goal of doing a word prediction. It's like all the thinking, like the whole thing is only trained on the job of doing a word prediction. So if you look at like an attention module, an MLP module, and you look at its output, there's papers written about how you can interpret the output of any neural network module as adjusting the word predictions. It's like if you look at like what the MLP outputs and you say, hey, where's the Eiffel Tower? And you look at the MLPs that like seem to be active when you're asking where's the Eiffel Tower, you can look at the outputs of the MLPs as just boosting the word prediction probabilities of Paris. It's injecting some vector into the residual stream, and then you think, what is you can do all the decoding to figure out like what is that vector doing? You can actually take the decoder head and like instead of sticking it on the residual stream, you can stick it directly on the MLP to say, what is this MLP like adding to the residual stream? What's it doing? And you'll see these interesting things. You'll say, see this MLP, which is very active, is like when you decode what it's injecting into the stream, it's like it's encoding this thing that says triple the probability of Paris. My God, it's Paris. You know, don't forget it's Paris. Eiffel Tower, Paris, 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 Paris. That's what it's saying, this MLP, right? That makes sense? And you know, it's fun. Or London or whatever. Whenever you have there's a lot of knowledge that you can see. You can kind of see this word prediction thing. But is everything in terms of word prediction? So there's some papers which like talked about how you can like scan over all the components of the neural network and understand how everything is done in terms of word predictions. But then we do see some representations where they don't seem to correspond to word predictions really well. If you put the decoder head on them, you get this garbage neuron, you get these garbage token, predictions that don't seem to correspond to anything that we understand. And so the experiment that Eric did is Eric, you can raise your hand. Okay, who's Eric? Yeah, I'm going to describe your experiment. Is he said, what if we take a representation vector and we do a reconstruction to find the smallest or the most similar, like the, representation vector, um, uh, the simplest unit representation vector that decodes to the same vocabulary. So you take the top 100 words and their probabilities that are decoded when you decode this concept vector, and you find another concept vector that decodes to exactly the same 100 words and exactly the same probability, but maybe throws away the rest of the junk, right? So if you think that the only thing that's going on is like word predictions, then by the time you get to the bottom of the top 100 words, then you're in the noise, you're in the zeros. Like there's like zero word prediction, power there, right? So if you take the top 100 things and you get another vector which throws away all the junk and just keeps the top 100 things, and that's where all the signal is, then that vector should do the same thing as the original vector. And so he went around to these interesting vectors that he had, these interesting neural signals, says, what if I just do that? And he's like, it loses this explanatory power for the phenomena that he had. So there's definitely concepts, which we'll talk about in a few weeks, which don't correspond to just word prediction things in these models. And so logic lens, like by that note, logic lens would be blind to those things. Right. So there are definitely, like, we know that there are things that logic lens would be blind to. That makes sense? So as is that maybe answers some of the skepticism questions here. It's like you are right to be skeptical, but in this very concrete way. Make sense? But and yet there's so much word prediction going on that it's like a good thing to look at. Okay. Okay, so oh, and then Guangyang, is Guangyang here?
Yep.
Yeah, what was your question?
But I guess the
I-
that's not overlap.
Did you get some answers already? You got your answers. Okay, cool. I just want to make sure people get their answers. There's more questions. Oh, Courtney, Aria, Yuchi, Christopher, Jasiba. Okay, there's so many questions. So there's this experiment that I want you to run, which is the natural language translation experiment. If you go to if you say something like this, if you say French and then put a French word and you say another language like Deutsch or Chinese, right? And then you ask the model like predict the next word. All these models, they know how to do translation. And so what I really want you to do is like run this, reproduce the Chris Wendler experiment, and then look inside what's going on in the neural network. And what you'll find is, on the way from translating from French, brewer, to Chinese, the same word, it goes through the English word, flower, in the middle, even though there's like no English in sight anywhere in the input text, which I thought, so Chris thought this was interesting. A lot of people have observed this and it suggests certain things. I don't know what you think it teaches us. Let's Courtney. Yes, what do you think of this experiment?
Maybe I'm not understanding the experiment.
Yes.
Confused. They make this claim that you pivot into like an English concept space.
Yeah.
Like not necessarily like
Yeah.
it's translating to English and translating back. It's more of like a conceptual English space. And I was wondering if that's really an artifact of how we're decoding.
Yeah.
Like
I think it
logic
is.
process itself is trained in English. So
Yes.
that's we're coming up with these decoded English.
Well, the logic process is trained predominantly in English. That's true. But it's also trained in all the other languages because like if you decode the very last thing, decode it in Chinese, decode it in French, right? And so but you're right, there's definitely a bias in the training for these models that were trained on the West Coast. They're like trained mostly in English. And so I think the interesting thing is that not the fact that it's English, maybe it's a little interesting that it's English, right? But to me, the interesting fact that is if you go from French to Chinese, if you go from like German to, some other language to Japanese or whatever, if you go from Spanish to Italian, like the example I like to use is in like Spanish, you say amor, and in Italian, you say amor. And so it's just got to like translate from amor to amor. It's like got to add a U or something. It's like almost the same tokens, right? But it goes through like love in the middle, completely spelled differently, completely like, morphologically different tokens. And and so to me, the interesting thing is that no matter what the language pair is, the thing that goes through in the middle is like decodable the same way. It's like decodable in English. And so whether the fact that it's English is important or not, I think that the interesting thing is it's like always the same, right? It's like some shared representation, right? That sort of answer?
Yeah.
Yeah. And Arya, you had a question about this setup. Do you have a similar question, Arya?
Good, mine was more on how, and the paper itself, the design experiment so that the next word as a single token.
Oh, I love this.
And I guess.
So what do you do? Yeah, look at these garbage tokens that we have. I don't know if we have any here, right? So there's there's this like little token duh, or there's like this token roid. What is this roid? I don't know what this roid is for, right? Or la. Like what is la? Like is la the beginning of something? Francois la. Like I don't know what la means, right? La is like you'll see this in some of the other examples I'll show later, right? But like a lot of times you see like one of the examples I'll see, I don't know if we'll have time to show you, I'll show you one that has to do with AI safety and like making bombs. And you can see that when it's thinking about like explosive power of a bomb, it has this logic lens thing where it says EXP. It's gonna like talk about explosions. But EXP is like, it doesn't say explosion. It's just like the first token in explosion. It could be first token in something like experiment, like something really innocent, experience, right? But so there's this question, like, how do we get insight on whether it's talking about like experiences or explosions? Like it just says X. So I think that's a really good question. You should look up Koyena's old paper. Future lens is a nice one, and then concept lens is another one. So some of the lenses wrestle with this a little bit to see if there's a way of going in. But we're going to just play with regular Logit lens, which is a single token prediction. But I like the question a lot. Okay, so then, but if you want to use like multi-token stuff in one of your papers, you should like read some of these other things. You can extend the method. There's things that you can do. Okay. Yuchi, Chris, Joseba, who are you? Raise your hands. Yeah, go ahead.
My question?
Yes.
Well, so my question is one of the things the paper touched on in the introduction here was that said, oh, well, if we're learning from our sources, we may be encoding anglocentric biases into the model itself.
Right.
So one question is, the model set, the paper gave a method saying, well, here's how you can surface like the tokens it's thinking about, but as far as actually making a rigorous claim about qualitatively is the model actually doing things like that, how would that actually work, right? Are you going to do qualitative analysis on the tokens, but then it's complicated by the fact that a bunch of them can be garbage too.
Yeah. Yeah.
So that was kind of one direction, because it's like, well, there might, there's going to be naturally representation of the things it's trained to recognize more, but it does like mean that there's a coherent bias in the in the human sense, right?
Yeah.
I think that's kind of a very difficult claim to substantiate.
Yeah, that's right. Right. So there's like all sorts of problems with Logit Lens as an experimental method. And so let me I'll leave your question open if that's okay. Because I think that it's worth thinking about what the limits are as we look at different experimental methods and see if I think that the real answer is, each one of these methods has some imperfections. It gives you a different view on what's going on. You end up trying to triangulate. Mhm.
Well, kind of follow because I got into this conversation actually yesterday was, even hypothetically, let's say there does seem to be at least in human eyes some troubling pattern or a bias.
Yes.
Tokens that appear in intermediate layers, but if in terms of the end user, what they experience either by prompt engineering or things like that,
Yes.
is that still even a problem?
Do we care? Right? I don't know, right? Does it matter? Does it matter that my language model is lying to me? What if it hates me, but then it pretends to like me? Is that okay? I don't know. I think it's a good question. Um, Guess it depends on how good an actor it is. Maybe by the time I die, I don't care anymore if it hated me. But if it might like sneak out in some behavior, maybe I do care. Maybe if it only reveals that it hates me when I'm not around, then maybe I care. Right. So I think it's a reasonable question. I think that intuitively people are like, oh yeah, I want to know what it really thinks. So we're sort of chasing that intuition, but there may be reasons that it's limited. More questions. Who else? Just have a yes.
See what it's yes.
Internal computation.
Our internal computation is
Yeah.
a way that we can understand.
Yes.
But then when we're trying to interpret it, it's just going through our own lens, which is not super scientific. So if I was thinking, what if you used an SAE and like trained it out the middle layers,
Right,
to kind of have a better idea of like is it actually English likeness that's
right,
happening in the middle layer, or is it something?
right. So I guess my feeling is that the essays are a little bit of a different technique. We'll talk about them next week, and they give you a different view on what's going on. Maybe it could give you a view into vectors that don't correspond to language that well. So it maybe be thought of as a good supplement to this Logit Lens technique, which is so language oriented. just a way of looking at other types of vectors that aren't necessarily as language oriented, maybe more abstract. So yeah, but I would tend to not combine the techniques too much, but look at them as complementary, right? But I'm not sure. Probably some people combine them as well. But that's just my intuition how to use these things. So essays and these vectors we'll talk about next week. And then okay, did everybody on the list get a chance to ask questions? Yes, Yuji.
Yeah, it's not like a real question, but it's more focused on the latent language paper.
Oh yeah.
Yeah, it's like I ask this because of my background, like I'm bilingual, so
Yeah.
most of the time I think in Chinese, but
Yeah.
sometimes I also think in
Yeah.
English.
Yeah, it's like weird. They like see and there's like bilingual models, like when
Yeah,
they're like equally trained in English and Chinese,
yeah, so I think
just like you.
no, like of course I'm more prefer Chinese.
Okay.
But like for the model, I think like about 90% of the training data is in English.
For this model, for Lala, yeah.
Yeah, so
But that's not true for the Quen. Well, we don't know. They don't tell us what it's trained on. But
so I think like maybe it's because like there are more training data in English, so it can in the middle layer is more like English token rather than other language. I think and they also use concept called token energy to say those tokens are not really English tokens,
right?
Different. I think
Right.
it's maybe because it's multi-language, so
right.
Maybe the model thinks in like different language, so the token in the middle layer should be like combined on different language.
Yeah.
There are different.
So I have a question to ask you back that has to do with this, and I would encourage you to do this in some of your experimental work. Is if you use Logit Lens on a model like Quen that was trained with different language biases, how does that change its output? I feel like there's been a little bit of work that looks at this, but maybe not enough. I think that some of these experiments, like the multilingual experiments, does it go through Chinese in the middle instead of going through English? Like, I don't know the answer to that. I don't know if anybody's ever published the answer to that. I think it'd be very interesting to know. And so I would hold on to some of your questions and like use that as an opportunity to like ask. It might be obvious questions to ask, but like nobody's asked them. We should look. Right? Does that make sense? Okay. So are we out of time? How are we doing on time? Am I out of time here? I'm out of time. Oh no. Okay, let me. I have 5 minutes. Okay, so screw all this stuff. Okay, so all right. Do I have 5 minutes or am I out? Am I over? I'm 5 minutes over. Okay. I'm exactly at the end. So maybe on Thursday I'll carve out a little time for people to try some of these things. Or you can try them at home, but I'd like to actually show you some of these experiments. I'll flip through some slides here so you get a little sense, but then you can tell me at the beginning of Thursday if you'd like to actually like go through them. But there's this nice notebook that I prepared. Oh, there's not enough time in a class. There's not, and then to do like example research. So like if you ask it, what's the capital of France? Then it says, oh, the prediction is A. The capital of France is a famous city, it's going to say, or something, I don't know what it's going to say, right? But you can see right before the last layer, before it says A, it's thinking Paris, 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 Paris. And then at the last moment, it says, no, I have something more grammatical to say. I'm going to say A, right? I don't know why. Here's like amour, going to amour, and then going through love, right? It says all these interesting stuff. Here's a pun. Why do electricians make good swimmers? Like, when does it get the idea that maybe it should stay current? It's like, does it know a joke? So there's these, you can take these kind of things like neutral versus funny context where you say, I used to be a banker, but I lost what comes next? Lost my job. That's dire. But what if it was in this context? What if it says, I used to be a tailor, but the job didn't suit me? The talk. I used to be a banker, but I lost my. And then you say, interest. Right? Get it? Get it? Get it, right? So you can run these through the model, you can see its internal thinking for when it gets like that. The punchline, right? And so okay, so there's a bunch of things like this. There's also a safety example that has to do with bombs and stuff. So if you're interested, think about it. On Friday, we could spend a few minutes going through these at the beginning and playing with them. But then remember on Thursday, get your like proposal for what you want to study, and your research project written down with your team, and then get ready to do a 5 to 10 minute presentation. My request to you is to do the I and finder. Tell us why it's interesting. Tell us why it's interesting. Tell us, like, point us to some background literature. Like, why do people in your field think it's interesting? Or why is it? Teach us why. That make sense? Okay. Thanks, guys.